Good afternoon, everyone, and welcome. I'm glad that you are here at the public defense of my doctoral research, which is officially titled A Study of Hydrogen and Methanol Combustion in Dual Fuel Engines. More easily, we can say that my research frames around the question, how are we going to make shipping CO2 neutral? The reason we want this is because our Earth is warming. This has huge implications for us. Glaciers on land and in the Arctic are melting and disappearing, and that is causing sea levels to rise. If we are not careful, it will rise by more than 1 meter by the end of the century. And that could cause problems since about 40% of the world's population lives in coastal areas. In Belgium in particular, we may have more frequent extreme weathers, such as the floods in Wallonia a few years back and the Kieran storm a few weeks ago. The reason for the rise in temperature is greenhouse gases. On this graph you can see the rise of CO2 in our atmosphere, and it has increased by 25% in the past 40 years. CO2 accounts for 47% of greenhouse gases, methane for a good 17%, and nitrous oxides for 6%. And then we have a 2% for the so-called F-gases used in, amongst others, bland extinguishers and refrigerators. The nitrous oxides is mainly released as a result of fertilization, and methane from our livestock in landfills or in the production and use of natural gas. CO2 is mainly released from our industry in power generation and in transport. In my doctoral research, I focused on marine industry, and this accounts for 2 to 3% of global greenhouse gas emissions. One question we can ask is whether regulations are needed to bring down those greenhouse gases. Currently, we emit about 50 gigatons of CO2 equivalent annually. If we continue business as usual, this will continue to rise, and by the end of the century we will have global warming of between 4 and 5 degrees Celsius. If all the new regulations are implemented correctly, our emissions will go down and we would be between 2.5 and 3 degrees. If all countries keep their promises, then just above 2 degrees. But we need to arrive at these curves to comply with the Paris Climate Agreement, so regulations are really crucial. Europe wants to be climate neutral by 2050, and they do that by implementing various regulations. In shipping, Europe's goal is to reduce CO2 emissions by 6% by 2030 and 80% by 2050. And that applies to ships weighing more than 5,000 tons and operating in European waters. And that's about 55% of all ships in European waters, and these account for about 90% of the ship's emissions in Europe. In international waters, the rules of the International Maritime Organization apply, and it recently updated its greenhouse gas strategy. That aims to be climate neutral by 2050, but for now it is not yet legally binding. Now the question is, how can we implement those regulations? What technologies do we have available for that? And here it is important to note that there are two markets for those technologies. On the one hand, you have new ships being built, but on the other hand, there's also a market for retrofitting existing ships. And that's because the lifespan of ships is more than 20 years. Now, before we can look for solutions, the question is, how are ships powered today? And that is mainly with petroleum products and internal combustion engines. More than 95% of ships are powered this way. Those petroleum products are typically heavy fuel oils, marine gas and diesel oil. We want to get rid of this combustion of products. And then when we start looking at alternatives, we need criteria to evaluate them. As a set of criteria, we can use the following. First and foremost, it is important that our solution is sustainable. And that means that we use a sustainable source such as wind or solar energy. Second, it is important that we have a scalable solution. Recall from the previous slide that we don't have one ship, but more than 100,000 ships. If we have a scalable solution, then that also means affordable. And the last criteria we have is the compactness of the solution. It has to be big enough, as we will see later. If we want to use a renewable energy source, that means we want to use wind or solar, for example. And then the first question is whether we can start using ships analogously like electric cars. So that means we install a battery electric solution in ships that we will charge directly by the grid. Whether this is feasible is best demonstrated by the next slide. This figure shows a patrol ship weighing around 4,000 tons and about 18 megawatt of power provided by engines. If we look at the volume occupied by the diesel tanks in the ship, we see that the diesel occupies this gray volume. Now, should we want to store the same amount of energy on the ships with batteries, we need this red volume. This is obviously not feasible, and we could also question whether the ship would remain stable. So, batteries are not an option, except for the very short distances. Now, how come we can't use batteries? We can see that most easily on this graph. This graph shows on the x-axis the energy density per kilogram and on the y-axis the energy density per liter. Now, if we put diesel here on this graph, we see that we are on the far right. Diesel has a fantastic energy density. For batteries, on the other hand, we are on the far left of the bottom. Batteries have a very low energy density. So for ships, we have to look at a different solution than electric. And this is why shipping is catalogued as hard to electrify. But then, if we can't use battery electric, what can we use? There are 4 technologies that emerge then. The first is the gas turbine. The gas turbine is an interesting energy converter, but has a number of drawbacks and is therefore not established in shipping, only for some niche applications. The second is using nuclear power, but nuclear power on ships is controversial and is therefore only interesting in niches such as in submarines. Third, we have back our internal combustion engine, but used in a different way. This is a very mature technology that has proven itself for many years, and also its supply chain is fully established. And then we also have the fuel cell. Fuel cell technology is a very promising technology, but its maturity is yet to fully build up, as is the supply chain. The latter two have the focus for making shipping sustainable. Both technologies will play an important role, but given the maturity of the internal combustion engine, it will play a very important role in making shipping sustainable. It is also this technology that I investigated in my PhD research. But then the question is this technology sustainable? Because a few slides ago I mentioned that this technology, together with petroleum products, is responsible for more than 95% of CO2 emissions in shipping. And to that, the answer is yes, provided that we use sustainable fuels. So we say, keep the internal combustion engine, change the fuel. And that reasoning is similar to today's electric cars. Because we also say that if it runs on electricity from coal-fired power plants, it makes no sense. The question is now how to produce sustainable fuels. Recall from a few slides back that we could not use ships as we can with cars. But actually we want to use the same source, wind and solar power, because these are our renewable energy sources. Now we have the ability to convert this electricity into hydrogen through electrolysis. Very briefly, this is actually the process where we put two electrodes into water, one positive and one negative. Water, which has the chemical formula H2O, that then splits into hydrogen and oxygen. And that hydrogen now contains all the energy from in the wind or the sun, subject to certain conversion losses. We can now start using that hydrogen directly for fueling, or we can feed that hydrogen to a synthesis process. If we also add to that synthesis process carbon or nitrogen taken from the air, from flue gases or biomass, we can now make any fuel we want. As a result, we then have so-called e-fuels, where the E stands for electro because the electricity comes from wind or solar energy. And with that hydrogen or e-fuel, we can now refuel our ship. When we burn e-fuels, which contain carbon, we do release CO2. But we have first captured that CO2, so we get a closed CO2 cycle, which is not bad for our climate. This way, we can distinguish two strategies to make the transport sector sustainable. The first is via direct electrification. We directly electrify our application, such as cars, and we directly charge them. And the second is the indirect electrification strategy. So in this, we are first going to convert the sustainable electricity into a fuel that we can then use in our application, such as ships that are difficult to electrify. But then the question is, which renewable fuels? And then we have to start with hydrogen, because that's the first product we make from renewable energy by electrolysis. And hydrogen is a very good fuel for engines and for fuel cells. But hydrogen has a disadvantage of having a low energy density. If we pull out our graph from earlier with energy densities by weight and volume, we had already diesel and batteries. If we add hydrogen under 700 bar, we see that its energy density is greater than batteries, but still much smaller than diesel. Even if we store hydrogen in liquid form, which means at minus 250 degrees Celsius, this energy does not increase much, and on the contrary, our fueling system only becomes much more complex because of these low temperatures. If we are going to apply this to our patrol boat from earlier, we would need this amount of tank volume with diesel, as we saw, and now we should add this amount of volume to have the same energy on board with hydrogen. So hydrogen will not be able to be used for long distances and high power, but only for small distances. As for example in this tugboat from the port of Antwerp with engines from ABC that sponsored my PhD. So that brings us back to this chart where we had already added the energy densities of batteries, hydrogen and diesel. And that leaves us with the question of what fuels we can start using for long distances. In theory, we could start producing diesel. The process is known to use carbon and hydrogen to produce synthetic diesel, but diesel is a very complex molecule. So that means it requires much more energy also to produce this molecule compared to more simple molecules. The simplest molecules then are methane, which is gaseous at room temperature, ammonia, which is also gaseous at room temperature, and methanol, which is liquid at room temperature. Now, one thing is clear, and that is that there is no one fuel that will replace diesel, but it will be a combination of different fuels. In our research, apart from hydrogen, the direct result of electrolysis, we have mainly investigated methanol because methanol scores the best across the whole line. It is liquid at room temperature, which makes life tremendously easy. It is biodegradable and it is a brilliant engine fuel. And that is why methanol is going to be a very important fuel in shipping. And this is also confirmed in practice. The past few years have seen the addition of many ships running on methanol. Recently, the first container ship, the Lara Maersk, was commissioned. The Stena Germanica has been running on methanol since 2015 and several Methanex ships since 2016. In recent years, several more demonstrations have been added, as for example the vessels part of the Fast Water project led by Professor Verhelst. A pilot boat in Sweden is running on methanol, and a tugboat from Antwerp will soon be commissioned on methanol. Now, most of these vessels are running on dual fuel engine technology. The reason that these vessels are running on dual fuel technology is because this technology has some very important advantages at the moment. It is possible to run either on diesel or dual fuel with methanol or hydrogen or the sustainable fuel. And that flexibility is crucial for operators and for the supply chain right now. If a ship arrives in a port with a dual fuel engine and it cannot refuel with methanol, for example, it can still continue its journey on diesel by tanking diesel. That way, the ship's risk of running out of fuel is avoided, and that also allows the fuel infrastructure to scale up. Visually, we can represent this as follows. On the y-axis, we have sustainability, and right now we are at the very bottom. Where we want to get is at the top, using engines that run entirely on sustainable fuels, because that's when we have the most CO2 reductions. To get there, we need the flexibility of dual fuel technology. So on the x-axis, we could add an additional parameter, and that would be, for example, the availability of the renewable fuel. The more sustainable fuels will be available, the more we will evolve towards the upper quadrant. And in that evolution, dual fuel technology will play a crucial role. And it is on this technology that I have been researching for the past years. Right now, as we just saw, we already have the first ships sailing with dual fuel engines on methanol, also on hydrogen. Those engines can be categorized as the first generation of dual fuel engines. The aim of my PhD research was to generate new knowledge in the development towards those second generation dual fuel engines. I did that in two ways: by making experimental measurements, and on the other hand by creating a numerical model. But before I can go deeper into my research, I need to do a recap of how engines work, because that will be crucial to understanding later what exactly I have been researching. So on this animation you see the internal of an internal combustion engine. You see 4 cylinders, and it is in these cylinders that combustion takes place over and over again. The cylinder transmits their up and down energy to a rotating crankshaft, and it is in this rotating energy that we are interested in because it drives our propeller. Now, if we zoom into the cylinder, we can say that we can distinguish in general 2 types of concepts from each other. The first is the diesel compression ignition principle. Air is drawn into the cylinder, which is compressed. And at the end of the compression, when there are high temperatures and pressures, diesel is injected. At these high temperatures and pressures, diesel self-ignites. And then we get the combustion of diesel, releasing its energy. The second concept is a spark ignition principle. This is typically applied to gasoline engines. Now the fuel, gasoline, is injected together with the air and is sucked into the engine. It is then compressed, and at the end of the compression we have a spark that ignites the mixture. This principle is also ideal for fuels such as methanol and hydrogen because they have a high octane rating. If we were to use hydrogen and methanol like diesel, that would not work. Those fuels, just like gasoline, would not ignite after being injected. This is because methanol and hydrogen have a very low cetane rating. And this is essential to use a fuel in diesel type engines. Now, if we want to introduce methanol and hydrogen into shipping and we still want to retain diesel operation, then we have to go for a combination of these two principles. And that combination is called the dual fuel combustion principle. In this animation, we see the dual fuel principle in action. We see that methanol or hydrogen is injected just before the intake valve, and diesel is injected into the cylinder. The mixture of air and methanol or of air and hydrogen is drawn into the cylinder and compressed. And at the end of the compression, diesel is injected, which then ignites the mixture. So the diesel actually serves as the ignition source here. We want to replace as much diesel as possible with methanol or hydrogen, but we still have to keep a portion of the diesel to ignite the mixture. This dual fuel solution is particularly interesting because methanol and hydrogen can be injected at low pressure. That makes it an easy solution for new build ships and especially for retrofits of existing ships. And that also makes it the most cost-effective solution among the various dual fuel methods. Now, to do experimental research, we need an experimental setup. When I moved from Engie to the Ghent University in 2017, my first task was to work with our technician and my professor to convert this engine to run on methanol in dual fuel. To do that, we installed several sensors on this engine. For us, crucial parameters to measure are pressure, temperature, and mass flow rate. If we know these quantities, then we can already calculate and understand a lot of what is happening in the engine. In addition to these sensors, we installed a methanol fuel rail, injectors, a methanol container and a fuel supply system, that means a pump, a data acquisition system and an engine control unit. Soon there will be a reception going on in our lab just next to the engine. So the people that are staying for the reception can take a look if they want to see all this in real life. Now, this was the end result, and on this engine we have done our initial measurements. We tested several engine speeds and several torques. This blue line gives the maximum torque of the engine. In an initial measurement campaign, we measured the yellow area and more specifically we measured the asterisks. In each of these points, we started from diesel operation and then we started by increasing the methanol amount. Every time you increase the methanol amount, you have to factor in that you have to decrease the diesel amount. Because ultimately, we want to compare pure diesel operation with dual fuel operation. And we want only one parameter to change. We don't want to change the other parameters like the speed and torque delivered by the engine. Because that way we can make good comparisons between diesel-only operation and dual fuel operation. In each case, we went until we couldn't replace extra diesel with methanol. This had several physical reasons, but it is also important to keep in mind that we can never replace all the diesel because then we would not have an ignition source anymore. In each of these points, we examine different parameters, a few important ones being the methanol energy fraction, the efficiency, and the emissions of NO and soot. Now, let's have a look at what these parameters are to be able to understand what follows. The methanol energy fraction is an important parameter that represents how much methanol energy is in the cylinder compared to the total energy in the cylinder of diesel and methanol. So for example, if this factor is 60%, then 60% of the energy comes from methanol and 40% from diesel. Then we also have the diesel substitution ratio, and this factor is very similar but only reflects how much less diesel we have to use and it says nothing about the amount of methanol we use. Typically, however, these two parameters are about equal to each other with a few percentage of difference. To calculate efficiency, we need to look at the total fuel energy we feed into the engine, on the one hand, and compare it with the power output at the shaft, which is measured. If we divide that power we measure by the energy input to the engine, we get the efficiency of the engine. And then the emissions, these were measured in the exhaust, and we measured typically soot and nitrous oxides. For our first measurement campaign, this has yielded the following results. We measured methanol energy fractions between 25 and 70%, which corresponds to a replacement of diesel with 17 to 67%. We measured higher efficiency in some points than in diesel operation, and relatively even up to 12% higher efficiencies. Typically, we had lower efficiencies at low load than in diesel operation and higher efficiencies at high load. NO emissions went down tremendously. On average, over the full range, we had decreases of about 60%. And soot emissions also went down tremendously, on average by about 77% over the entire area we measured. We presented the results of this campaign at CIMAC in 2019. And this triggered several new research questions. The first question was whether we could change the methanol injector location to reduce the cost of this solution. That research was published in Fuel Communications. In a second campaign, we investigated whether it is beneficial to have water in methanol, which could be interesting, for example, to reduce the production cost of methanol. And those results were published in Fuel. And then third, we investigated how we could replace more diesel with methanol, because the larger this percentage is, the more CO2 emissions we can obtain. The more CO2 emissions we can reduce. To investigate this, we played with three engine parameters, with the intake air temperature and pressure, and with the exhaust gas recirculation. We presented these results at the SIA Congress in Capri this summer. Besides experimental research, ABC was also interested in numerical research. In 2018, they started developing their dual-fuel hydrogen and methanol engines installed in these two tugs. Now, you should know that if you do experiments on the engines in these vessels, that you will soon consume 50 liters of fuel per hour per cylinder. And in these vessels, there are typically 2 megawatt V12 engines, which means that we are consuming for each engine about 600 liters per hour. So at €1 per liter, you come at a cost of more than €600 per hour. Measurement campaigns easily take several days to weeks, so the cost of fuel alone adds up enormously. So that's why ABC asked us to develop a dual fuel combustion model. We did this, but to do that we had to develop a number of new things. These included a new diesel ignition delay model, because diesel is now injected into a mixture of fuel and air, and not only in air. The results of this were published in Fuel earlier this year. And then we implemented all the new submodels in a fully integrated dual fuel model developed in GT Power, and the results of this model were presented as well at the SAA Congress in Capri this summer. Now, on all the results of my research, I cannot go into detail. Therefore, I have extracted some results to present to you. For example, to increase the diesel substitution by methanol, we have investigated the following. So on this figure, first of all, you can see the one-cylinder dual fuel combustion with the location of methanol injection and diesel injection. We can also further see the air intake, which are linked an extension to on this figure. To see how we could replace more diesel, we played with a number of parameters. The first two parameters we played with are intake air pressure and temperature. Because when we change the air pressure and air temperature, we also change the temperature and pressures in the cylinder. And these in turn affect the combustion of methanol and diesel. You could compare it to an exercise test of an athlete on a bicycle in a certain room. If we increase the temperature in this chamber and keep the pressure constant, would the athlete's performance improve or not? So very similar, we investigated the effect of these two parameters, the intake temperature and pressure, on the amount of diesel we could replace with methanol. This is because that amount is limited by a number of phenomena in the cylinder, plus we also always have to maintain a certain amount of diesel because diesel is the ignition source. We found that by reducing the pressure, it did not give a positive result on the diesel substitution, but with higher temperatures we could achieve a 5 to 10% higher diesel substitution. The third parameter we tested was EGR or exhaust gas recirculation. This basically means that you start returning some of the flue gases to the intake, which has a positive effect on a number of parameters such as NOx and NOx formation. Here we have seen that we could achieve up to 7% higher diesel substitutions. Then next we tested water in methanol. This is interesting for several reasons. First, the production cost of methanol can decrease. We can see this on this figure where we saw the methanol production process. In the synthesis process, hydrogen and carbon react with each other to form methanol. Now, in one of the last steps of the production process, the methanol, which has a purity of 90% methanol, is further distilled until when the remaining 10% water is also purified out, such that we get very pure methanol. The question now was whether we could skip that last production step, because then we can reduce the cost. We saw that from a diesel substitution point of view, that was not beneficial. With every increase of about 10% in the methanol blend, we saw the substitution of diesel with methanol going backwards by 10%. Now for NOx formation, it was beneficial. Here we saw up to 30% decrease in NOx when we added up to 50% water. And this compared with pure dual fuel operation. Then in one of our first experimental campaigns, we tested the methanol injector position. So here we have the one cylinder animation with the methanol injection and the diesel injection. Now in an engine we have multiple cylinders. In the Volvo Penta engine we have 6 cylinders in total. That means that we have the same process taking place 6 times, with the methanol injector just before the intake valves each time and with the diesel injector in the cylinder each time. The air comes from one big intake manifold and the air in it via the intercooler and turbo from the atmosphere. That intercooler is there to cool the air because after compression in the turbo, the air is seriously heated. Now, our question was whether we could limit the methanol injection location to one location just after the turbo. That way, we could place methanol injectors in a more accessible location than just before the intake valves. Now, when we did our comparison, we saw that it was not beneficial for the substitution of diesel with methanol. For NOx, it was not favorable either. Only for efficiency, it was favorable because of the higher temperatures in the cylinder. Now, to obtain all the previous results, we have conducted experimental research. This means that we first had to build a test setup. Then we could start taking measurements on it, and then we had to add new systems to that engine to make new measurements possible. On the one hand, a heat exchanger and a wastegate for controlling the air temperature and pressure, an exhaust gas recirculation system to send the exhaust gases back to the intake, an addition of injectors in the intake to test the different methanol injector positions. Now the question is whether it is also possible not to make measurements but to make predictions through calculations of what the engine would do. In this way, as mentioned earlier, we could save fuel costs but also time because such measurements take a lot of time. ABC was particularly interested in this to develop a dual fuel combustion model for their engines. In my PhD, I therefore focused as well on the development of a dual fuel model, initially for the geometry of the DZ engine family. But my model can also be used for other types of engines with some adjustments. We built that model in GTPower, a simulation software used by many engine manufacturers. To do that, we need to make all the components of the engine digital, starting with the intake manifold and the methanol injector. Next, we have the intake valves. Then we have the cylinder connected to the crankshaft. In the cylinder, we have a diesel injector, and then after combustion, the exhaust gases go through the exhaust valves to the exhaust collector. Now, GTPower is a strong software for established fuels such as gasoline and diesel, but not for new sustainable fuels such as methanol and hydrogen. So that is why we had to create several new submodels to get good predictions. One of those new submodels is the diesel ignition delay model. So here you had the animation of the one-cylinder dual fuel engine. Now, because because diesel is injected in a mixture of air and methanol or of air of hydrogen, this is different from how the injection occurs in a traditional diesel engine. In a conventional diesel engine, we observed in the earlier animation that diesel is simply injected into air, and that has an impact on the ignition delay. Now, what is the diesel ignition delay? When diesel is injected as a liquid, it must first transition from the liquid phase to the vapor phase and then mix with air to ignite. The time between diesel injection and diesel ignition is called the ignition delay. This is very, very short, typically on the order of less than a millisecond. Now, if we inject diesel into air, we are injecting diesel into a different environment than if we inject it into a mixture of methanol and air or hydrogen and air. And we saw, especially with the presence of methanol, a much larger delay in dual fuel operation. And that longer delay in diesel ignition could not be captured with the models developed for diesel engines. Therefore, we had the need for a new ignition delay model, and we developed that. In addition to a new submodel for diesel ignition delay, I also had to create new data for the laminar burning velocity. The laminar flame speed is the speed at which the flame front moves in the cylinder. You can compare it to an explosion, for example, a car exploding. When it explodes, it does that at a certain speed. And it is that speed that is important when predicting the pressure buildup of such an explosion. And that speed, it varies depending on the pressure and temperature in the cylinder, so we need a lot of such data. Now, if turbulence is also present, then that creates an additional burning velocity. We replaced the turbulence burning velocity model in GTPower by a more accurate one. Now, all these models together are crucial because they indicate when the diesel starts combustion and also how quickly the methanol or hydrogen will burn. And that speed determines the pressure buildup in the cylinder and thus the force delivered to our rotating crankshaft, which is then transferred to our propeller. So an accurate representation of all these physical phenomena is crucial to have a dual fuel combustion model. As a result, we obtained the following pressures, where the solid lines are measurements and the dashed lines are predictions. The blue curve is with 25% methanol energy, and the green curve is with 50% methanol energy. That means that at one operating point we have 25% of the energy coming from methanol and 75% of the energy coming from diesel in the cylinder before combustion. And at the other operating point it's 50-50. The red indication is at top dead center, and this is when the volume in the cylinder is minimal, so when the piston is at the top. We see that as we approach this point, the pressure builds up, and after this, combustion takes place. So we have an even stronger pressure buildup here, despite our piston already moving downwards. Now, our predictions, our dashed lines, fall within 2 to 3% of our measurements, which is within a range of 5%, which is typically a threshold to say that we have good predictions. Also for hydrogen, we see the same good agreements with the curves again at 25 and 50% hydrogen energy fraction. And these results bring me straight to the end of my presentation. We have seen in this presentation how important it is to have regulations because they give us the objectives to work towards. And on the other hand, we saw how important sustainable technology development is in that story due to the limitations of battery electric applications. We also saw the importance of the combustion engine with sustainable fuels, and more specifically how the strategy falls under the indirect electrification strategy. And finally, we saw the importance of dual fuel technology in the transition of shipping to sustainable engines. We need flexibility while the fuel infrastructure can build up and deliver the dual fuel technology. And that is delivered by the dual fuel technology. Then we saw that we could replace up to 70% of diesel with methanol without too many fundamental adjustments to our engine. Just figuratively speaking, by adding methanol injectors in the intake and controlling these injectors. We achieved high efficiencies and low NOx and soot emissions. With our experimental investigations, we saw the following things. When we used increased intake air temperatures, we could increase the diesel substitution, and also when we used EGR. The best methanol injector location is just before the intake valves. And methanol in water is allowed, but we have a trade-off. The more water we allow in methanol, the less diesel we can replace with methanol. And we want this fraction to be as high as possible. The numerical results has yielded some interesting new submodels, such as the diesel ignition delay model and the laminar and turbulent burning velocity model. We then implemented these new submodels into a dual fuel combustion model for an ABC engine and tested it, and that gave us pressures predictions within acceptable limits. So that was it. I thank you very much for your attention.